I'll give you a minute or 2-minute warning.
Sure, thank you. So yes, today I'm going to talk about how we can use the moon to understand about the meteoroid environment at 1AU. I'd like to acknowledge my co-authors, Mihai Hirani, Sasha Kemp, and Zoltan Stranovsky, and also 3 more that got cut off, Eberhard Grun, Ralph Srama, and Jürgen Schmidt. So, as Mihai told you, LADI had a dust detector called LDEX orbiting the moon for about 6 months. The reason that we could even make measurements is because the moon is constantly being bombarded by micrometeorites. So while Earth shields the surface because of the atmosphere, they ablate, as Zoltan was just talking about. At the moon, they freely impact the surface and generate these wonderful plumes that we were able to detect. They are grouped into 2 different kinds of impactors. We have the Meteoroid Streams, and those are characterized by collimated beams that we've detected at Earth that all seem to be originating from the same parent body and have orbital elements very similar to the original parent body. And there's sporadic meteoroids. Those are pieces of material that do a variation. So highlighted in the 4 blue lines are the 4 meteoroid streams that really seem to make an effect on our detection, not just by impact rate, but as I'll show in a second, actually the geometry of it really lined up. The northern toroids are curious because this is mainly from one plume, this huge plume we flew through, and that's going to be a whole other topic of study. The Geminids generated the largest response. Those are pretty much the strongest performers at Earth, and at the moon, that held to be true. There's one curious thing in that we detected, as Tony talked about, we detected a stream on March 25th that was not observed at Earth, and since we detected it, and UVS saw it, and it seems to be somewhat correlated in geometric in space, we believe it's possible that it could be an additional stream. So, one of the neat results that we were able to get out of the data was we can actually measure the mass distribution of the ejecta and therefore the mass distribution, more or less, of the dust on the surface, all without landing. The reason is we measure impact charges, but by some work done by Jürgen Schmidt, it turns out that that impact charge pretty much directly relates to the mass of the impactor. The distributions are the same. And so we found this is our distribution of impact charges, and it's about as textbook of a power law as you can get. And the slope is about -1. It's minus 0.9 in cumulative mass. So by flying over the lunar surface, we can tell you the size distribution of tiny grains at the surface because they're regardened. Here is the exosphere, the lunar dust exosphere we measured. A couple things of note. One, it's asymmetric in the apex, anti-apex direction. So the apex in this is up, anti-apex is down, and the sun is on the left. Not only that, it's a little canted towards the sun. Both of these were a bit unexpected, and we wanted to understand what's going on here. So here's a little more qualitative to show you again that as a function of local time, where 6 is the apex direction, you see these bumps in density as a function of different altitudes. Well, we can ask, well, what does the current state of knowledge tell us about what we should expect? Here is, as a function of local time, the predicted mass flux hitting the moon. This is from engineering meteoroid model developed for the Constellation program to see how much stuff was going to hit the moon. And we used that to determine, hit an orbiting spacecraft, but we used it to see how much would hit the moon. So you can see the anti-helion and helion source, shown by AH and HE, are about symmetric. The apex actually has a little dip in mass flux, and the anti-apex is significantly lower just because things have to hit you in the back and catch up to you. But then we thought we're not measuring what's hitting the moon, we're measuring what's coming back up. And so when you fold in, using the work from Koshny and Grun, the velocity dependence, so the amount of the stuff hitting the moon, the yield, the stuff that gets kicked back up is highly velocity dependent. And because the stuff that hits you in the apex direction is primarily retrograde, and it's on about 60 kilometers per second when it impacts you, that's able to actually make up the difference and enhance the apex direction as having the most detectable impact ejecta. So one of the other neat things is we wanted to see, okay, now we realize there's this preferred direction. So the apex direction, and maybe a little canted away, for some reason we have more stuff being generated. We wanted to test and see if there's any other information we could use to verify that. So what we did is look at, for a period of 4 months in a quiet period, so from October to the beginning of January, there were a lot of showers, but we want to look at the sporadics. So from January to April, we looked at the very smooth over impact rate as a function of time. What you can see is it's sinusoidal, and it has about a characteristic amplitude change. And so we looked at where do those occur. So shown in the red dots are all the points at which we reached our maximum impact rate as the moon moves around the Earth. And shown in blue are the times the times in which it reached a minimum. And what you can notice is, just like every orbit, we saw an enhancement a little from the apex canted towards the sun. Well, when the moon is smashing into whatever's hitting us, at that phase, we see the most impact ejecta. And likewise, when it's running away from that direction, we see the least. What we can conclude from this is we can get some measure of actually the mass yield as a function of velocity. This has never been done before on a scale the size of the moon. We can use the moon as this big laboratory that's swinging around the Earth and modulating the velocity of the incoming particles. And from that, oh shoot, this is, again, an older slide. This is supposed to be v to the 3.0 plus or minus 0.7. So we can measure the exponent on that velocity dependence. All right, so the next thing we looked at is the response of the lunar surface to meteoroid streams. So here are the 4 known ones that generated the biggest response: Northern Taurids, Geminids, Quadrantids, Omicron Centaurids, and then this mysterious one that is not recognized. So today we're just focused on the Geminids. So here's a top-down view showing the density enhancement of the Geminids meteoroid stream. You can see this arrow is a cartoon, but this is actually accurately portraying where it's coming from, and we got about a factor of 2 to 2.5 enhancement in the density of the local exosphere in dust. One of the things we wanted to do is see if there's anything we can learn about this meteoroid stream. So, as you've heard about, sometimes we would get groupings of particles. So every time we make a detection, an impact plume ejected, and we just grabbed one of those particles. But every once in a while, we fly through one so dense that we get 10, 50, 100 particles in a single, what we were calling burst. And so what we did is we tried to quantitatively group these impact events into bursts. And the way we did it is using a Poisson statistic analysis. So it turns out our impacts follow roughly a Poisson distribution. For 0.7 microns, we got an impact about every 7 minutes. And so using probability, we can say if we got 2 events within 10 seconds compared to one every 7 minutes, those probably came from the same event, and we're going to group them together. And so we group them according not to time, but to probability. So here shown is the radiant impactor for the Geminids. The bullseyes right here, these are angles on the surface out from the moon. The color strip is the Lati orbit, colored for only times that LDEX was on. And the color represents what we think is the theoretical density of plumes, so based on both the time and the location on the surface. The black dots show groupings of events that we grouped in 10% probability. And as you can notice, it's pretty much isotropic throughout our entire orbit, which we should expect. 10% is not a very low probability event. So then what we can do is start to slide in probability. And so here is probability 10 to the minus 3.5. And you can see these impact events start to tighten. You see no impacts on the hemisphere opposite of the Geminids, which is reassuring. As we continue to slide, get down all the way to 10 to the minus 5, these impact events really, these bursts really tighten right down onto the Geminids radiant. So we can plot this as a function of the probability. Shown on the x-axis is the minus log of the probability. So that's just the exponent without the minus sign, where increasing this number is decreasing probability in log scale. And shown here are if we take every little burst and we shoot an arrow out from the moon, we can try to get an estimate of the radiant that the Geminids hit, or whatever meteor stream. So this is the right ascension, which is roughly the angle this way, and the declination, which is roughly the angle this way in the ecliptic. It's actually in J2000. And you can see that as we slide the probability, as it decreases and decreases, the error reaches a global min and then goes back up. And what you can notice is we actually hone in on the actual radiant parameters shown by the dotted line for the Geminids. So what we can do is by orbiting, it's pretty wild, by orbiting many, many times and just detecting a bunch of plumes, we can actually tell you where in the sky something hit this airless body. Not only that, we can tell you the timing of this event, and we also looked at the other streams. Now, this is a highly geometric sensitive measurement. So if an impact hit above our latitude, it's a little tougher to get the radiant. But we can get the time. So this shows the L and the E means Lati and Earth observed. We're able to get accurately the Geminids' time and radiant dimensions. And then for the other streams, we could accurately, within about 6 hours, estimate the peak time as well for the unknown. So, in conclusion, we were able to successfully measure the ejecta cloud in dust of the moon. And it turns out that the moon is this very neat large-scale laboratory. So nature set up this really cool experiment where you take very high velocity particles, you hit the moon, they're amplified, so the moon's this big amplifier, and our detector is able to detect the response. One of the neat things is that at Earth, we have a few different ways to detect meteoroid streams. We have visual and radar, but this represents now a third new way to understand the meteoroid environment at Earth. Not only that, if we were to go to another airless body where we don't have this ground infrastructure, you could actually use an airless body as a big sensor. It's a huge amplification factor. The lower the gravity, the more the amplification. And you can use that to amplify the response of the meteoroid environment. And you can tell maybe if you want to land something or put people, when's it going to rain rocks and when's it not. So thank you very much for your time.
For the total Doug Curry, University of Maryland. For the total impacts, the Gemini seemed to have a peak, a double peak. There was a peak before you would have made your blue mark.
Are you talking about the impact rate plot?
All the way back to the beginning.
Yep.
There
we go.
See the second peak in front
this
of the.
Or this?
Oh no, down below.
This one right here?
Yeah.
That. So the Geminids is a very sharp distribution in time. Within a day and a half, it, at least based on Earth zenith hourly rate profiles, it decreases by about an order or two of magnitude. It turns out that in this region right here, I haven't marked, but right after this, there's this meteoroid stream called the Pi Pupids. There's Montecerids. There's a ton of other streams there that are minor, and they hit in different places. And so it's possible that this is from a different stream. If I were to show you every single meteoroid stream, it gets really busy. But we don't believe that this is the Geminids.
All right, so thank everybody, all the speakers, and